For two-dimensional motion in a gravitation field, an object traveling in a plane with a vertical distance y and horizontal distance x with only the force due to gravity has, given the initial position r of 0 equals x naught y naught, initial velocity v of 0 equals u naught v naught, position vector r of t equals u naught t plus x naught, and then negative 1/2 g t squared plus v naught t y naught, velocity vector equals u naught, comma, negative gt plus v naught. So how do we even get to these? Where do these come from? We know that force equals, a force vector equals mass times acceleration. Vector 0, negative mass times gravity, and that equals the mass times the acceleration. Dividing both sides by m, we get 0, negative g equals the acceleration vector. So to solve this to find velocity, we're going to integrate both sides with respect to t. So we get the vector 0, negative gt plus some constant vector equals the velocity of t. We know that v of 0 equals vector u naught v naught. So if we have 0, negative g times 0 plus c equals the vector u naught v naught, that means that c equals the vector u naught v naught. So now we have, plugging that in for c, we have velocity equals the vector 0, negative g of t plus the vector u naught v naught equals v of t. And combining those vectors, we get u naught comma negative gt plus v naught equals v of t, which is what we had. So how did we get position? Well, we took the derivative again. So integrating again, we get u naught t negative 1/2 gt squared plus v naught t plus a constant vector c equals the position vector r of t. We know that r of 0 equals x naught y naught. So if we plug in 0, we get 0, 0 plus c has to equal x naught y naught. So that tells me that c is x naught y naught. We have u naught t negative 1/2 gt squared plus v naught t plus the vector x naught y naught equals r of t. And when we combine these two vectors into one, we'll get our original position vector that we were trying to find. So that's how we came across those. Given an object traveling in a two-dimensional gravitational field launched at an angle at alpha, the object has time of flight, t equals 2 magnitude of v naught sine of alpha over g, range v magnitude of v naught squared sine of 2 alpha over g, maximum height y times time of flight divided by 2 equals magnitude of v naught sine alpha divided by 2g quantity squared. So where do these come from? Well, they come from, let's say we have the graph of a trajectory. So in a two-dimensional gravitational field, our trajectory is going to look like parabolas. Well, at time equals 0, the velocity vector is tangent, so this is v naught. So if this angle right here is alpha, then we can complete this triangle and we get the initial velocity, this red vector here. So this side, little v naught, equals sine of alpha equals the length of vector v naught divided by this side v naught. So to solve for v naught, we get length of that vector times sine of alpha. So we have vector v naught. We know the y coordinate is v naught, length magnitude of v naught sine of alpha. And similarly, u naught is equal to length of v naught times cosine of alpha. So that's our initial velocity, and we know that our equation for velocity at time t equals the vector u naught negative gt plus v naught. So substituting these in, we get magnitude of v naught cosine alpha negative g of t plus magnitude of v naught sine of alpha. So this is the velocity for the object. So the position, since we start at position 0, 0, our initial position, r of 0 is 0, 0. That's where we oriented ourselves, just to make things easy. So we know that our position equals u naught t plus x naught negative 1/2 gt squared plus v naught t plus y naught. So plugging in u naught, v naught, and x naught, y naught, we get the vector magnitude of v naught cosine alpha times t plus 0 comma negative 1/2 gt squared plus length of v naught sine of alpha times t. So to get our time of flight, we want to know when the vertical position equals 0. That's where we have landed. So we need to find when our y-coordinate in our position equals 0. So we have negative 1/2 gt squared plus magnitude of v naught sine of alpha times t equals 0. And factor out a t. So 1/2 gt plus magnitude of v naught sine of alpha equals 0. So we get time equals 0. So we get time equals 2 magnitude of v naught sine of alpha over g. And that is going to be our flight time when we hit the ground at the end. So to find our range, we need to plug this in to our x. So to find our range, that will be the x value, the horizontal distance, when t equals the end of the flight time. So we plug this equation in for t, our flight time in for t, and we get v naught cosine of alpha times 2 v naught, magnitude of v naught, sine of alpha over g. So we have magnitude of v naught squared times 2 cosine of alpha sine of alpha over g. And 2 cosine alpha sine alpha is equal to sine of 2 alpha. So this gives us v naught, magnitude of v naught squared, times sine of 2 alpha over g. And that will give us our range. And then to find our maximum height, we need to know that's where our derivative is 0. So that's going to be where our velocity up here equals 0. So our maximum height is going to occur when we know that maximums occur when derivatives are 0. In this case, we have velocity is our derivative, and we want the y, or the height, velocity to be 0. So where it is negative gt plus magnitude of v naught sine of alpha equals 0. So we get t equals magnitude of v naught sine of alpha over g, and we want to plug that into our position, negative 1/2 g times magnitude of v naught squared sine squared alpha over g squared plus magnitude of v naught sine alpha times magnitude of V naught sine alpha. Let's go ahead and square that over there. G. So we get some cancellations. One of these cancels there. We get negative 1/2. We have V naught squared sine squared alpha plus V naught squared sine squared alpha all over G. So that gives us V naught squared sine magnitude of V naught squared sine squared alpha over 2G. And that's going to be our maximum height. So let's find the position and velocity vectors. Graph the trajectory, determine the time of flight, range, and maximum height of the object for a football thrown from the initial point 0, 0 with an initial velocity of u naught v naught equals 15.3 meters per second. So first of all, let's find our velocity. So v of t equals the vector u naught t equals vector v, the velocity vector equals u naught negative gt plus v naught, and gravity, since we're in meters per second, is negative 9.8. So we can plug that in too. And our position, r of t, is u naught t plus x naught, which is 0, negative 9.8 over 2 t squared plus 3t plus 0. 9.8 divided by 2 is 4.9. So we have our position vector is 15t, negative 4.9 t squared plus 3t. Graphing our trajectory. Here's what we look like. Now we need to determine the time of flight, range, and maximum height of the object. So to do that, we need to find alpha, and we also need to find the magnitude of V naught. So let's go ahead and find the magnitude of V naught first. And that is going to be magnitude of V naught equals square root 15 squared plus 3 squared equals square root of 234. And next we need to find sine of alpha. So our initial velocity goes upward. We know that its horizontal component is 15, its vertical component is 3, and we have a right angle, and we know that this is square root of 234. So to figure out this angle, we can use, so we have tangent of alpha equals 3 over 15. So the inverse tangent of 1/5, and that is 11.31. So alpha is 11.31. So now the time of flight equals 2 times the magnitude of the initial velocity times sine of alpha, so sine of 11.31, all over gravity, which is 9.8. gives us 0.61. So our time of flight equals 0.61 seconds. Then our range is equal to square root of 234 squared times sine of 2 times 11.31 all over gravity, So 9.18 meters is our range. And that looks about right, looking at our graph. And then finally, our maximum height is the magnitude times sine of alpha all squared over 2 times gravity. So our maximum height is 0.459 meters. And going back to our graph, that looks right. Three-dimensional gravitational fields use the same formulas for range, time of flight, and maximum height, and are very similar to two-dimensional motion, but have that added extra dimension. So let's say we have a golf ball hit east down a fairway with an initial velocity of 40.025 meters per second. There's a wind blowing to the south at negative 0.7 meters per second squared. So in this case, we're starting off with 0, negative 0.7, negative 9.8 as our acceleration, because we have this wind blowing to the south at negative 0.7 meters per second squared. To find our velocity, we integrate both sides, and we get the vector 0, negative 0.7t, negative 9.8t, plus a constant equals our velocity. And our initial velocity is 40.025, so we'll find that c is in fact that vector. So we get 40, negative 0.7t, negative 9.8t plus 25 is our velocity. To find our position, we need to integrate again. So we get 40t, negative 0.35t squared, negative 4.9t squared plus 25t plus a constant vector equals the position at time t, and we'll find that c equals the 0.000. So that's going to go away. Here's our velocity and our position vectors. So now we're ready to find our time of flight, range, and maximum height. So we need the magnitude of our initial velocity. So that is going to be 40 squared plus 0 squared plus 25 squared. That gives us 47.17 is the magnitude of our initial velocity. We also need to find our angle. So if we have a right